thanks for coming, everyone. My name is Tim Griffith. I'm a principal engineer working for the Amazon retail business, rather than Amazon Web Services, based out of New York. And I'd like to talk to you today about how we changed the way that we worked in terms of our orchestration to solve two key problems that we had by using Amazon Kinesis. So what I'd like to go through this session is, first of all, a little bit of background about how the Amazon retail business works in terms of how we actually take listing information in from our vendors and sellers. I'd like to go through the challenges that we faced as we've grown as a business and why we needed to do something differently. And then I'd like to dive into the method that we took and why we took it in terms of using Kinesis as our back-end orchestrator. And so I'd like to look at, first of all, the cost mechanics, why we did it from a cost perspective, why we did it from a distributed coordination perspective, as well as other benefits that we got from working with the distributed log. And one of the things that I hope you take away from this session is that Kinesis is not just an analytics engine. It is very much a full distributed log, and some of the things that we can do with that are fantastic. So that's really the motivation, if you like, for this talk for me. So I want to go through how we got 2/3 of our cost reduced, as well as simplifying the processing semantics of the downstream systems that we were using this orchestrator to compose over. The architecture that we came up with, something that looks like this, so has a gateway. That gateway has a settings or SLA configuration. So when someone submits work to the system, it will go and work out contractually when it should execute that work and encode that information into a handoff to Kinesis, and then return that contract back to the user. This is a very important thing for us, and we'll get into why as we go forward. The handoff from Kinesis goes to the back-end worker, where it uses processing configuration to work out, first of all, what is required before that process can actually run, and then when it goes to dispatch it, which process instance should run first. So this gives us a sense of priority as well as ordering. We then talk about handing that work off to action handlers. If anyone's worked with SWF, it's very similar in terms of a handler. And then those in turn will also use Kinesis to respond back to the orchestrator. And when the process is done, it will finally communicate back to the user. So a full asynchronous model. Now, in order to understand why we went and built this, we need to really start off with a little bit of information about how listings work on Amazon.com. So first of all, we always start with a product. So this is something that we're selling. And we're really talking about the facts around that item. So we need to identify it. That identifier is unique to a particular seller or merchant. And so they will have some kind of stock keeping unit or ID, and they will provide a series of facts about the item. So it can be very simple things, such as what type of product, how to locate that product, what color it is, product dimensions, so size, weight, etc., who made it, brand, a whole series of facts that help make the product interesting and the correct product discoverable for our users. Moving on from there, we obviously not only want to describe a product, we want to be able to sell it. So there needs to be some kind of offering condition, which says how much we're going to sell it for and when that price is going to hold. So it might be that we have a normal price, we might have a promotional price, we may not be able to sell it until a certain period in the future. Finally, we also have the ability to relate items. So if you think about products, some products inherently have sort of groups of the same product. The example we'll use today is a shoe. So if I'm selling a branded shoe, there are going to be lots of facts that are the same, but yet I still need to have individual products for each size and each color, because I need to be able to identify when someone has ordered a size 7.5 black and green shoe that I send them the right product. So we still need these detailed specific products, yet at the same time, we probably don't want to think of them as all specific products, because we want to be able to help the user discover these things. So If we were to build this from scratch, you might think, given the AWS components out there, that actually this would be really easy to put together. So shared nothing is easy. We could imagine that if we start from our sellers, that we'd have a big API fleet, and then from our API fleet, it would then push down into a NoSQL database. We need to get that NoSQL database into a form that can be searched. Obviously, people aren't going to search by my particular stock keeping unit, my primary ID. So we're going to need to get it into a reverse index. Obviously, cloud search is up here, but as you've heard recently, that could easily be Elasticsearch now. And we have DynamoDB streams that would allow us to plug that in seamlessly, especially with Elasticsearch. So we could get up to a reverse index quite easily, and then working in from the customers, visiting the website, we'd imagine, well, there are lots more of them, so we'll have an even bigger API fleet. We don't want to hit that reverse index for every single request. We imagine there's going to be lots of commonality, so imagine a huge caching fleet. But we can come up with a fairly simple architecture, albeit one that operates at very large scale. So does this equal Amazon? Well, maybe the right-hand side, reasonable representation, but the left-hand side, not so much. So let's go a little bit through why. Now, we can start off with the fact that we do have the world's largest selection of products, and we have the largest number of sellers on those products, enormous numbers of sellers. And so if we imagine that we're building a service that's going to show you each unique seller's version of a product, and imagine doing a product search. So if I'm searching for Nike trainers, even if I put the shoe size in, maybe I want to see what colors are available, and I'm going to end up having enormous numbers of exactly the same product listed, pages and pages of them, potentially tens of pages. It makes it actually very difficult to find the actual product that we want. So from a user experience perspective, we want to provide a single product. We want people to be able to work from there to see, okay, what sort of configuration around this product? What kind of instance of that product am I particularly looking for? And then finally, from there, to be able to go to, well, who is selling this, to work out who I should actually buy the product with the specification from. So we built the concept of the single item detail page. And keeping with the shoe analogy here we can see a Nike shoe. You can see that there are, on the right-hand side, a large number of different colors and a large number of different sizes. Now, the important thing, and the reason why we've pulled this together as a single page, is that you can see that the core information about the product, so the description that this is a Nike Free Trainer 5.0, and the sort of bullet points at the bottom that describe some of the core facts about this, they're going to be the same no matter what size that shoe is, no matter what color it is. Now, we then pull up all of those children in order to provide this sort of matrix, sparse matrix of what colors are available. And then if you choose the color first, it will show you what sizes. If you choose the size first, it will show you what colors are available in that size. So we've moved from a sort of a grouping that has been pulled together of items into the specific item. And then finally, once we've got that specific item, we'll start off with who we think is the best seller to buy that from. And we're trying to make that on behalf of the users. So, if they have a Prime account, then maybe it's one which has free Prime 2-day shipping. And obviously, there are other sellers, and we will, if this was a little bit wider, we would show that the other sellers on the right-hand side of the page, where you could choose other sellers. So we've tried to bring it to product selection first, so that we do discovery first, and then who you're buying from second. Now, this makes things a little bit more complex from the architecture's perspective. So whilst indeed we do receive, essentially each seller has their own catalog, we need to bring that information together. So we need to, first of all, standardize the information and validate it. The important thing behind standardization is because in order to bring things together, we need to match them. And if we don't have standardized values, it'll be difficult to match them. We're going to match them and say, OK, you appear to be talking about this particular Nike product. OK. Now we end up with lots of information from lots of different sellers describing that product. Some of it can be contradictory. Some of it is overlapping. But what we have is an abundance of data. And what we want to do in this position is we want to do data reconciliation. We want to have a look at who's provided the information, the quality of the information they've provided, and for each attribute, for each product fact, We want to choose what is the best value or the best set of values so that we come up with the best, most complete overall description. And then once we've got that, we want to store that down by its own proprietary identifier, and this is the Amazon catalog ID. Now, because we've done this, when we think about those other pieces of information, so the offer piece of information, what I'm going to sell it for, as well as the relationship information, this has to be relative to the Amazon catalog. So we have to wait until we understand, for my SKU, what does that match to, or what is that created in the Amazon catalog, before I can then put my offer. And that offer has to be relative to that ID because of the structure that we have. As you saw on the previous pages, we need to be able to navigate first by product, and then once we've got the product selected, which is the Amazon ID selected, we then want to navigate the offers relative to that ID. So this requires top-level orchestration. Fundamentally, we need to process product first, and then once we've processed product, we can then process some of the other data types. And this is a simplified version, obviously, but it gets the main thrust of our problem space across. Now, the easiest and cheapest way when you're dealing with an orchestrator, especially as the majority of our information comes through product feeds or product templates, is to do the orchestration in aggregate. So imagine that I have a feed that has 10,000 things in. I'm updating my catalog to Amazon. It can be reasonable to do all of the product first. So let's say out of those 10,000 updates, 5,500 of them are product. And then once I've done all my products updates, I can then do all of my offers and all of my relationships, potentially at the same time. Now, that can obviously be not very responsive, and running through a feed processing platform isn't very responsive if we have a user interaction. So if someone comes in to do a correction, they come in through the interactive user experiences, then they want to do it individually, and they want a much faster update time. So in this situation, we want to have one-by-one orchestration. So we have both, and the orchestration approach differs a little bit as it stands in order to manage that. So we've solved this problem? In fact, well, we solved this problem early in the century, so around about the turn of the century. So what changed? Well, we took on a lot more sellers and a lot more products. We are a much, much bigger marketplace than we were 15 years or so ago. And with that, we end up having this kind of pattern. So we can see that as more sellers come in, lots of those sellers, they don't distribute their products evenly. We actually end up getting more and more sellers on a subsection of our products, particularly popular products. So we might end up having multiple coming in. And the problem with this is that we can get a very large number of sellers on a given product. And this, as you can see, is not shared nothing. This is very much bringing data together. And that gives us a problem. Now, we originally were optimistic in how we handled this. So we would try and update the catalog, and we would see if it's changed underneath us. And if it had, we'd just reread it and go and apply our change to it again. Now, this ended up, a reasonable time ago, ended up getting rather significant in terms of its overhead. And so we ended up moving to pessimistic sequencing. So we would physically say, I am going to update this item, lock that item, and then proceed doing our update. Now, what that does is that sequences or serializes each of those updates coming in. So if I'm the first person in, absolutely fine. If I'm the second person in, I have to wait for the first person's update to finish. If I have 200 people coming in, and I'm the 200th, I may have to wait up to 200 other people to complete their processing in order for my processing to get in. So because the number of people that are updating at the same time is not very deterministic, we ended up having very unpredictable performance. When are we going to be able to complete this work? Depends on how many other people are updating the same product at the same time. It's not something that we can really control. Likewise, the feed processing, being that macro orchestration that's doing in layers, it ended up compounding the performance problems. If I have problems with multiple products, then they end up being added together often. And then if I get to a problem with a relationship afterwards, then that time is also accumulated. As a result, the volatility in terms of how long it will take to process a feed when it's submitted to us is even greater than in a one-by-one situation. We also had a problem in that we were running these two different orchestrators. So one-by-one behaved in a different way to the feeds-based system, and as a result, we actually had some sequencing issues because someone might send a feed in. The unpredictable performance means that they feel it should have completed by now, but hasn't. So they go to the one-by-one experience because it's important, and go and send in that update. Now, that update can then overtake the feed, and so we now have to cope with a situation whereby we don't take what was in the feed, especially if it was different, and overwrite the more up-to-date one-by-one submission. So the final one for this is that besides users taking it into their own hands because their update hasn't gone through, we also need to cope with the fact that many people will want to understand where their stuff is. Why has this not reflected on the site? Why has this not processed? So it leads to regular calls, regular contacts from the users, which is obviously painful for them, and of course it's painful for the development team. So from this, we ended up with a series of requirements that we had to work through. The first of which, from the client, we need to be able to reason when the work will be done. And we need to be able to check for a progress of a submission when we haven't met our expectation. But the most important one of these is to be able to give the user a pretty solid guarantee of when we will actually complete that work. Now, we'll get into part of how to achieve that in a bit, but one important thing from that is that we already established the feed processing platform increased the volatility, and we had a sequencing problem, so this pretty much came down to we needed to be able to do it one by one for everything. From the services that were being orchestrated, we wanted to be able to guarantee those services that they were being called with the most important work that was available, and whilst maintaining strong ordering, so that those services don't have to cope with every single one of those services doing an effective version or similar in order to try and work out what the correct representation of the work was, and to handle out-of-order updates, because it gets expensive again in terms of storage. We also have a series of situations, as we saw with that funnel in a few slides ago, that we end up having lots of work that's on the same key. Now, in many of the cases for us, that work could actually be done in a single interaction. We could take that work together. So we want something from our orchestration platform that can actually give us batching. And then finally, from the non-functional perspective, we want to be able to run as fast as possible. A big part of being able to meet contractual guarantees is by being able to make the platform really fast. The other part, we want it to be cheap. We don't want to make going to one by one, which gives us the fastest possible, to compromise us on cost. In fact, ideally, we'd also like to try and reduce the cost of the platform as we go through. So this is where we started from. So if we move on to our target architecture, and then we simplify it a little bit, we end up with an interaction whereby we have the seller, and the seller needs to be able to submit to the orchestrator and get a guarantee of when this is going to complete. The orchestrator then needs to make sure that it executes work whilst preserving ordering and sequencing, ordering and priority, sorry, and then over a series of services. So the first and obvious answer to this is, well, can we just use SWF? Now, in our particular case, and these numbers are illustrative, let's say that we're running at 5,000 transactions a second. We are a big, high cardinality, high volume update service. So if we were running at 5,000 transactions a second, that would translate to about $1,800 for execution. And then the additional task would be another $900 per hour, so $2,700 per hour. Now, that works out to nearly $24 million a year for the orchestration platform. And that's definitely not going to be doing it as cheap as possible. That's significantly raising costs. So we have to start off saying that this isn't viable for us. It would be really nice to have an out-of-the-box service, but what we're doing is somewhat unique. We'll be operating several orders of magnitude out of what SWF is designed to provide. So we need to step into this ourselves. So the first way that you would do an asynchronous orchestrator, if you were to go and step in and build it, is you keep durable state for your asynchronous continuations. So whenever you send out work to a client, You need to retain the state of what you sent out to them so that when they eventually complete and call back to you asynchronously, you can hydrate that process, you can join the resultant information, and then you can move to the next step. We can decouple a handoff both to the services and the seller by using something like SQS. And this is a fairly simple, fairly rudimentary implementation, but we can work out that this is going to scale for us. We can cost it out, and we get down to something which costs around about $188K a year. So this is a lot more viable. Obviously, there's a lot more build for us. We would have to build that central orchestrator. We would have to manage and own it. So there's definitely significant dev cost and ops cost. But this is at least viable. However, we did feel that we could do better and that we wanted to investigate further. So the first thing that we started looking at was, well, one of our big costs was handing off to the services. And we'd seen the Kinesis pricing, and the Kinesis pricing looked good. So we went and said, well, can we go and use a Kinesis worker out to the services? The services are going to be working in batch anyway, most of the time, or in small batches, so it makes sense. We can substitute in reasonably easily. And this was interesting, because this gave us a substantially lower cost for that telemetry. We actually dropped from approximately $8.50 an hour to, by substituting out that second phase of SQS, it dropped to about 40 cents an hour. Now, that's a big deal. That's an order of magnitude cost savings. So we were pretty excited about this. But then we started pushing further. So the next most expensive thing is storage. The biggest cost there is Dynamo. So we started having a look at what we actually needed from our process. So storage has two functions in an orchestrator. The first is to enable the asynchronous continuation of the process. This is critical in order for your orchestrator to work. The second is an audit function, being able to go back in at a period of time later whilst you're retaining that information and being able to see what happened, or at least what the final state was. Now, in our situation, obviously, the continuation is critical. We must have that continuation of state. We must be able to handle a transient failure. Now, the audit, on the other hand, is more nuanced. There are many other strategies we could use for audit. We didn't strictly need the audit that would be naturally guaranteed by writing into the store. So we then started to look at, well, we actually don't really need key addressable storage. We need all of the information to route to the same place. We need it to be durable enough so that we can continue our processing and that we can remove audit from the situation. And of course, Kinesis has the concept of affinity. And that affinity means that I can write a process, and as long as I define that process ID or that natural key, that it will get routed to the same shard. And even if that shard worker was to fail, that I would be able to fail onto a new shard worker, and I would get the information through in the same sequence as it had occurred and processed in the first shard worker in the second shard worker. So this is pretty powerful. So we started saying, well, can we just get rid of the storage entirely? Can we move to a pattern like this, whereas rather than writing into the storage before sending off, we'll do all of our writing through Kinesis. So we will write when the process is first given to us into Kinesis. That will then be read by the orchestrator backend working as a Kinesis client. It will then in turn dispatch across to the services, and when they complete, those services again will write their responses through Kinesis. So we're gaining our durability through the log. Now, that was really promising, but not there quite yet. So first of all, Kinesis, or at least at the time that we were doing this, only allowed 24 hours of durability. Now, that's not true now. It could do 7 days, and 7 days would have been enough for our worst possible case scenario. So maybe this first bullet point isn't true anymore. But the second one, the time it takes to reconstruct 24 hours of data, bear in mind that we're writing in gigabytes every 5-10 minutes, that this is terabytes of data to pull back and rebuild. This is very, very expensive. It would be 7 times as worse if we were to rebuild across the whole 7-day slice. So it's still not really feasible to just use Kinesis as a durability mechanism. So we needed something else. Now, we can obviously say, if we're pulling up all of the in-flight process state into memory, which is the plan, that we can have many, many gigabytes of storage, and we can snapshot it. But snapshotting has basically two approaches to it. We use immutable structures, which add a large amount of object overhead, and therefore reduces the efficiency of each of our shard worker considerably. Or we can use a stop-the-world snapshotting operation, which is much better in terms of memory density, but then it leads to volatile performance, especially if we had 10, 15 gigs of heap that we are looking at snapshotting in order to write it down. This could be a very significant pause, 20, 30 seconds, and that could mean that we're going to breach our quality of service guarantees because the system is itself unpredictable. So we really don't want to do a stop-the-world operation. And if possible, we don't really want this really dense, or rather really sparse data packing with immutable data structures. So what can we do? Well, the actual pricing API of all things gives us a clue. So the pricing has the caveat that the hourly shard rate is based on 1 megabyte a second ingest, the rate that you can put, and 2 megabytes a second that you can read. For the same price, you get 2 reads for every single write. So this gave us the idea of, well, why don't we just read it a second time? So we have the orchestrator, which never does its snapshotting, and we have a process that looks almost exactly like the orchestrator, an archiver, which just deals with the snapshotting for us. And so this is really powerful. We can do some really interesting things with it as well. So we don't need to run the archiver at the same size of fleet as our main orchestrator, because we don't need it to keep up that aggressively. In fact, we can get our archiver to have a subsection of the fleet and literally rotate through the shards. So it can be a much smaller fleet. It's also really interesting to see that actually we can test out our recovery process. If we write our orchestrator and our archiver in such a fashion that they share a common code base, we're effectively constantly checking our recovery strategy because the orchestrator will recover in exactly the same way as the archiver will build up our information. So there are a few things that make this a little bit more difficult. So the first is the Kinesis client library only supports a single checkpoint. We'll call that the high watermark in this particular case. Now, that checkpoint is not going to reflect what we last snapshotted. That's going to be something over here. We'll call it the low watermark. So we have a previous snapshot sitting there in S3. So we need something that, when we actually recover, can build up to that new snapshot. In other words, it can start up at the low watermark, it can recover forwards, and then at some point, it will realize that it's hit the high watermark, which is the last thing that was actually processed, that we now have that snapshot as a good basis point to start our processing forward, and then move our processing forward. And in the case of our archiver, that processing forward would simply be to write down the S3 state and to write the new low watermark, essentially to set the low watermark to the previous high watermark. Now, the other thing is that we need to make sure that we're making the same decision in both our archiver as well as our orchestrator. In other words, the orchestrator's decisions, which are dependent on the data, dependent on things like capacity of what it's going to dispatch, need to be reflected actually in the archiver itself. And the only way to do that is to use what we call closed input monotonicity. So not only must it process in sequence, it needs to make sure all of the inputs that it would use to make a decision are also flowing through that Kinesis stream, which then means any change to those inputs or scaling requirements are going to be received in exactly the same way into the archiver, so the archiver can make exactly the same decision based off its reading of the stream. So for instance, if we're looking at what the replication latency is off our Kinesis stream here, or how many outstanding items if we're snapshotting from an SQS handoff, we need to make sure that those kind of back pressure statistics are actually fed into the stream itself. So another requirement that we have to build, a slightly more complex service consumption contract, but something that we think might be worthwhile. So we went and costed it out. And the really interesting thing from this, and you can see just how much it reduces in the cost, that we end up reducing to around about 1/3 of the cost, so around about 40%. So here, we end up with a little over, or a little under $81,000 for something that was going to cost us $188,000 before. And the really big mover here is that Kinesis is now doing all of the heavy lifting, and it's actually extremely efficient, both cost efficient as well as processing efficient for us to do so. We end up spending a little bit more in terms of our memory instances. As you can see here, the dominating factor of this costing is actually moving from compute instances to memory optimized instances in order to make sure we have sufficient capacity. But at the same time, we end up with something which is substantially cheaper. And the snapshotting to S3 with a reasonable rotation period ends up being negligible. Likewise, the Dynamo usage for writing the high watermarks. So this was really powerful for us. But in all honesty, this was only one of our objectives. If it was just this, maybe the architectural complexity wouldn't be worth it. However, we got a whole series of additional benefits. So first of all, let's just say we did manage to show we could run as fast as possible. We've got a paradigm that allows us to go down to 1 by 1 for all interactions in a single orchestrator, so one set of infrastructure. And we've done our absolute utmost to reduce the cost of being able to run at that 1 by 1. But what else? Well, we mentioned that Kinesis works by affinity. So how can we exploit that? How can we use that to do something useful? So let's start with a very simple key and scenario, and this is a very important and common scenario for us. We have a low priority update. The feed comes in, it's a low priority feed, and it makes an update on a whole set of items, including our really important item with the impossibly long key to remember there. So it makes the version 1 update at time t. Now, this doesn't get scheduled for a long period of time. Here we can see that it's due to execute at 2:30. And it has a low quality of service. So this isn't going to get executed anytime soon. Then the user might realize that actually this item is critically needing some kind of change. And so they might go into the interactive experience and do a quick change, which they want to be done as fast as possible and as high priority. So we end up with a second update coming in. It comes in a little bit later, but we need that update to be applied after the first update because we want to preserve ordering. But we also want to make sure that updates goes through as quickly as possible. And we don't want the downstream systems to have to cope with out-of-order updates because there are a lot of systems that we would need to go and put the same kind of logic into all of them. We want our orchestrators to be able to handle that. Now, this is actually very easy because if we say that the affinity key is the key component there, so that updates on the same item or the same product go to the same shard, we can guarantee that the shard worker will put them in the same memory. And so making a dependency in memory is really easy. We just say, OK, we already have one. Imagine a hash map style lookup. OK, we'll put this as dependent behind it. Then we can see that actually we have a risk. Our high value one is due to complete nearly an hour before our low value one. So what we need to be able to do is say, OK, this isn't going to work. We're actually at risk of breaching that SLA. And at the same time, we can't just drop the first value because the first value might actually have the second one as an incremental on top of the first. So all we can do is we can simply realize that this is a problem, and we can just promote forward the SLA as well as the quality of service. So we can make sure that that blocking item is going to execute in such a fashion that we can actually proceed forward. This is incredibly important. And most importantly, this is incredibly easy to do in terms of an in-memory structure off the shard. Very, very simple indeed. Doing the same on a remote call and scheduling, essentially doing a coordination via a NoSQL store is a lot more expensive, both to code as well as to operate. So we can see that we have now got a solution that gives us both ordering and priority, and in fact allows us to honor both without having to give up on either. What else? Well, one of the big things we mentioned is the ability to exploit batchability. We want to be able to say, actually, I can do multiple changes on the same key at the same time. OK? So imagine that we've got the first version ready to dispatch here, AEV1. So we can go and move that down to dispatch. Now, logically, that satisfies, or could satisfy if we're doing a little bit of look ahead, the next version, if there's something else dependent on it. We can simply check our dependencies at the time that we're going to dispatch and say, if this was already completed and it's a batchable task, is there anything else that could run? Well, in this case, V2 can. And then we can continue unwinding down that list. We can evaluate V3. Now, in this case, V3 has another dependency. It's not possible for us to dispatch V3 at this stage because V1 still hasn't been processed. So There's not much we can do there, but the whole point is that we can very easily walk a very simple in-memory tree structure in order to provide this batching logic. It's actually extremely easy to implement this on the back end. So we've now gained from this the ability to, clicking too fast. So we've now gained the ability not only to order and prioritize, but we've also gained the ability to batch. Now this is huge for the system because especially in that reconciliation step, it's almost exactly the same cost to run it for one item as it is to run with, let's say, a couple of hundred inputs. It can do that at almost the same cost. So by being able to do batching, the system holistically gains much more throughput, and it gains much lower latency because there's no queuing. So this was a massive win for us. But we still had one more thing that we needed to get through, and that was predictable execution. So we've tried to remove bottlenecks with batching. We've managed to get everyone down to one by reducing the cost. But we still need to go a little bit further than that. We still need to be able to provide a mechanism that can actually guarantee a quality of service to our users. So we need to give them a time that this will complete. Your work will be done at this time, together with a contractual guarantee that we will actually be able to make that. So working backwards, we'll say, let's give them an instance SLA. Imagine a UTC timestamp and a quality of service against that, our confidence internally that we will be able to make that. So imagine the highest possible quality of service. We will guarantee you this even if we're down to 1% capacity. Whereas the lowest quality of service, it's essentially best effort. We will run if nothing else is running. However, expect there to be disruption, a standard smoothing or prioritization. So we will then choose to order based on the SLA, and then we will make selective decisions as to whether or not we should dispatch in order to meet that SLA, or at that point of decision, whether or not we should actually just drop the item. Not drop permanently, but drop as in breach the SLA, record that it's breached, potentially let the user know that we haven't been able to meet their SLA, and then schedule into the next interval. So if we have a look at that as an example, again, very simple data structure in order to ensure that we are looking at the most close to dispatch or close to breaching SLA first. We simply do a min priority queue, bog standard data structure. So the one on the right has the lowest time. I realize it's a little bit difficult to read. So it's 13 seconds past the minute. The one after it is 14 seconds. The one after it is 15 seconds. So we're going to evaluate the dispatch on this item. We're going to look across what other items exist behind it. We're going to see whether or not they are more important or less important than us. So for instance, imagine that quality of service, the higher it is, the more important. We can see that there is something with a high quality of service, 2 items behind it. And so by it dispatching, it might be putting that higher quality of service item at risk. So we need to factor that in. At the same time, between the two, there is an item of lower quality of service. So if it was to decide not to dispatch the quality of service 3 item, and then we were to dispatch the quality of service 2 item instead, because it wasn't putting the highest priority at risk, then we wouldn't have done the right thing in terms of prioritization. So what it does is it goes and takes all of those inputs behind it, and it doesn't have to calculate it each time. You can calculate this as an incremental heuristic, but it can go and understand what's behind it in the queue to generate a weighted probability of dispatch. And then it'll do a dice roll. It will go and work out whether or not it should actually dispatch that item. Now, of course, as mentioned, we have to do things in a deterministic fashion so that our archiver will make the same decision as the main orchestrator. So in this particular case, we need to make sure that we seed that random dice roll by a piece of information, such as the sequence ID, the last read sequence ID, before it actually runs the dispatch. So we need to make sure we're consistent. But once we've done that, we can choose to dispatch if it passes the dice roll, or if it doesn't pass the dice roll, we can just say, okay, it didn't meet the SLA. We've deliberately chosen to breach it so that more at-risk things or more important at-risk things behind it can execute in its place. So that's one part of the system, but we also understand that a lot of our work comes from feeds. and that we really want to be tolerant of bursty work. We don't want to penalize with aggressive throttling in order to apply fairness. So we really want a system to be able to smooth out traffic and at the same time prevent people from just abusing their quality of service, so just saying that everything is the most critical it could possibly be, and still ultimately defend against denial of service, defend against the whole system being flooded. And the way that we went about that is we go and have an algorithm that looks up configuration, a contract as to what our commitments are to that user for a given priority. We work out what essentially is the prorated TPS as a maximum base time, and we'll see this in a worked example in a second, to work out what we should use as our basis time. Bear in mind that everything is operating as UTC timestamps. And then we should go and see whether or not we can actually issue that SLA, or whether we are too far in advance, whether we have given too many permits, if you like, or too much capacity at that priority level, and that we actually need to downgrade to the next level of quality of service because we're oversaturated. And of course, if not, we'll actually take that calculation and we will go and issue that out. So if we go and do a quick example, and this is a little complex, but trying to make it as simple as possible, imagine that we have a piece of work that comes in now. So the now time is 0. We have a high watermark time because we've not actually dispatched anything else at this priority, ever apparently. And so our base time is going to be whichever is bigger out of the now time and whatever our last high watermark was. So that's obviously going to be 0. We're then going to add our SLA time, which is going to be 2 seconds because this work is coming in as something in the high priority bound. And so we're going to contractually commit to completing this work 2 seconds out, so at 2 on our timeline, and we're going to give it a quality of service of 5 from the top SLA. And then finally, we'll calculate our new high watermark. And that's based off the previous base that we used, plus the prorated TPS. Now here, we've unrealistically said that we're only going to give 1 transaction per second to this client at that priority. So to prorata transactions per second into UTC interval time, we simply take 1 over the transactions per second. 1 over 1 is 1, so we've calculated our new high watermark as 1 second in the future. Now imagine a second item comes in. So the calculation is very similar. The now time is still 0. However, our high watermark time is 1 because it's taking the current high watermark as to the issued contract. So the maximum of those is 1. However, we're saying that actually 1 is greater than the maximum lead time. We're being very stingy here for the sake of a simple example. We wouldn't actually have this little smoothing. However, we're saying that the maximum time the base can get ahead of our now time is 1 second. And now that it has reached that, we're saying, well, we can't actually issue this contract. So we're going to have to roll down to the lower priority. So now we go and reconsider at the lower contract. There is no high watermark for the lower contract, so its base ends up as 0. Oops. That's it. I've lost a clicker. Guess I'll do it this way. So we end up taking our base of 0, and then we look up our SLA time. Now, our SLA time is much longer for the lower priority, so we've given a 5-second SLA for this one. As a result, it will end up scheduling all the way out at 5 seconds in the future, and it will have a lower quality of service. So it will have quality of service of 3. And finally, our base calculation needs to be redone. So in our particular case here, because we get 2 transactions a second rather than 1 transaction a second at the lower priority, what we end up with is doing 1 over transactions per second again. So we end up scheduling that for half a second in the future. Now, if we were to have a third piece of work coming in, and this shows how it flips back, and that third piece of work was to come in half a second in the future, so it comes in at half. When we go and run our base calculation, max of 0.5 and 1, we can see that that then gives us, well, we'll take the maximum of those, which is 1. 1 is only half a second of the time that it came in, half a second ahead, so it's within the max lead time. We can issue at our top quality of service. And so we can then go and calculate our SLA, and we can move our base forward again. So the interesting thing here is that our second piece of work is scheduled much further out than our third. And this could be a big problem. Right? Imagine that those two pieces of work just so happen to be on the same key. We'd have now inverted the order of them. But again, this is covered by the fact, as we covered previously, that it will still go to the same shard, it will go to the same in memory, and it will realize that, okay, 3 actually needs to be executed sooner than 2, and it will promote up the ordering and the timestamp so that actually it would end up executing 2 and 3 in line to meet 3's issue quality of service. So again, really powerful what we can get out of the back of the Kinesis library. So this gave us a much better position to reason about when the work will be done. And that's all we really have time to go through in terms of the main session here. So I can't really go through how it also allows us to trace in terms of audit. We do have that capability as well, but unfortunately it makes the slides run long. So I'd like to end by saying, by putting Kinesis at the core of our architecture, we managed to, number one, reduce our TCO considerably. We managed to internalize, for all of the services that we were composing over, ordering and prioritization. We allowed those services to be significantly simpler, to remove all of the out-of-ordering logic that they were doing and the storage that they needed to do it, which actually reduced cost from the services that we were orchestrating over. So it wasn't just a cost reduction for the orchestrator, we actually ended up getting value out of our composed services as well. We ended up recovering a significant amount of cost and complexity there, which was really important for us. And we gained new capabilities. So we gained that ability to batch, and that was incredibly powerful for us. That's actually a real game changer to our cost mechanics. So all in all, it was a very significant thing for us. And the important thing for this, chances are most of you won't need to build an extremely high TPS orchestrator. It's fair. But what hopefully you've taken away from this is the power of what you can do with the distributed log. You know, it's a very basic but very powerful building block. It is much faster to scale than things like Dynamo. You know, you can split shards and join shards in minutes rather than a couple of times a day. So you can do a lot by having transient storage with Kinesis. Okay, so thank you everyone, and I've got about 5 minutes for questions if anyone's got any questions.